Kobayashi geodesics in AG, the modular space of abelian varieties. So let me first state very quickly what is a Kobayashi metric. So basically it's the attempt to define a hyperbolic metric on any complex domain. So therefore we take 2 points in our complex domain, and then we define something called a chain, which are points in a unit disk, and then we define some maps, some holomorphic maps from this chain to our original points, which satisfy certain transformation conditions. And then we just take the Poincare metric on the chain points in our unit disk, sum over them, and then take the infimum of all chains. And so this, first of all, is only a pseudo-distance, not really a metric, but if we are in the right space, which is Kobayashi hyperbolic, then this actually becomes a metric. So luckily for us, AG is a Kobayashi hyperbolic, meaning the Kobayashi metric becomes actually a metric, and a geodesic is simply a geodesic with respect to the Kobayashi metric. So what are some examples for Kobayashi geodesics in AG? So there are 3 examples I want to introduce today, one of them being Shimura curves, the other one Teichmüller curves. I will explain what this is later. And the third one being curves which come from upper half plane modulo a triangle group, where a triangle group is coming from the reflections of a triangle and described as a matrix. And so we can now look more precisely what properties these examples have, and we see that Shimura curves and the ones coming from triangle groups can appear in a compact or a non-compact version, while Teichmüller curves are always non-compact. And now we want to ask which Kobayashi geodesics are non-compact. And there's this very nice theorem by Müller and Viehweg, and basically states that every non-compact Kobayashi geodesic factors through the locus of remultiplication in AG. And this makes things very easy now. Not very easy, but significantly easier. Then we can reduce our question to the modular space of real multiplication. And this is precisely a Hilbert modular variety, where we have G many copies of the upper half plane, modulo SL2 OK, where OK is a maximal order in some number field K. So now our question can be reformulated by now we are asking what number fields have a Kobayashi geodesic. And now we can just start from the beginning and ask, okay, what is the G equals 1 case? Well, this is then precisely the Hilbert, the modular curve, so this is not really interesting. What about G equals 2? So then which number fields have a Kobayashi geodesic? And the first answer would be all of them. For the simple reason we can just take the diagonal in our Hilbert modular surface, and this is a Kobayashi geodesic. It's also a Shimura curve. So we want to exclude Shimura curves in our considerations. So then we just asked, okay, what Kobayashi geodesics do we have that are non-Shimura curves? And the answer is, well, all number fields, all quadratic number fields have these, and these are Teichmüller curves, which was proven by Müller that for every quadratic number field we have a Teichmüller curve. And now is the next question, what about G equals 3? So this is not really known yet. So the non-compact Kobayashi geodesics we have for cubic number fields are Shimura curves and one Teichmüller curve and its twist. I will ignore to explain that now. And but basically this one Teichmüller curve that we have lies in this one cubic number field, which is generated by the 7th root of unity, and it's totally real. And we don't know anything about any other number fields. So the next question would be, what about other number fields? Are there any other cubic number fields which have a Kobayashi geodesic which is not a Shimura curve? And this is kind of the leading question for my project. So how do we do it? Well, first of all, we have to include the Teichmüller curve into a Hilbert modular variety and then try to describe it with something. Well, something will turn out to be modular forms, which we can then apply to different number fields. And so let me show you concretely what this means. So first of all, I mentioned before, I want to define what a Teichmüller curve is. And a Teichmüller curve is a curve inside the modular space of curves, which is totally geodesic for the Teichmüller metric, which also coincides with the Kobayashi metric in this case. And we can also think about them differently, namely by just taking the upper half plane modulo a subgroup gamma of SL2R, which has to be a lattice. So there's a little obstruction, namely by the definition. I just said that Teichmüller curves, first of all, lie in a modular space of curves. And we want to say something about AG, but this can be solved very quickly by just considering the Torelli map, which maps everything to AG. And then we want to consider the locus of free multiplication inside. And we can also do this directly by considering something which we call a Hilbert modular embedding, by embedding the Teichmüller curve directly into Hilbert modular varieties. So now let's apply this to our Teichmüller curve. So first of all, I want to rename the Teichmüller curve and call it the heptagon Teichmüller curve for the simple reason where its origin comes from. Namely, as I mentioned before, it's generated by the triangle group 2, 7, infinity, which is the reflection group to a triangle, which after certain kind of reflections results in a heptagon, which motivates the name heptagon Teichmüller curve. And this lies in the total real number field of the seventh root of unity. And if I write in as a quotient, I get this quotient here, and I get, if I look at the fundamental domain, I get this fundamental domain, which looks, or half of it, which looks very familiar to the modular curve that is known, simply for the reason that you can also write a modular curve as a triangle group where you change the 7 to 3, and then you don't have pi over 7, but pi over 3 here. And now let's try to embed this. I don't want to go too much into explaining this picture, but basically we have now a Hilbert modular threefold, meaning we have 3 copies of the upper half plane. So this is how the modular embedding looks in the first copy, in the second, and in the third. So there's a lot happening, which I can't explain for now, but this is to visualize that. And so now we have a description of our Teichmüller curve inside the Hilbert modular threefold. So the next step is to describe it via modular forms. So I just quickly want to recall what a Hilbert modular form is. This is basically your average modular form, with the exception that we now have a vector of weights, which can have different values, or they can be all the same. Then we call it parallel weight. And which modular forms do we take? So we use some coming from the Siegel modular varieties, and then embed them via a Siegel modular embedding to the Hilbert modular case. And so first I want to introduce theta constants, which are basically theta functions, with the exception that we evaluate them on v equals 0. And these are modular forms with parallel weight 1.5. And the second kind I want to introduce are theta derivatives, where we derive in one of the directions that we have, and then evaluate at v equals 0 again. These are modular forms with weight 1.5, with the exception for the ith value, there it becomes 3/2. And so, yeah. Now to my result. So I showed that the heptagon Teichmüller curves lies in the vanishing locus of this even theta constant with that nice characteristic, which actually is kind of coming from the fact that the heptagon curve lies in the hyperelliptic locus. So meaning there's always one even theta constant which is vanishing because it's hyperelliptic. Due to Mumford. And the second result is that this also lies in the vanishing locus of these 7 odd theta derivatives in the third eigendirection. And this is more coming from the properties of a Teichmüller curve, and that it vanishes, the eigendifferential vanishes. And yeah, I don't want to go too much into this proof. And the next step would be to apply this to different number fields, and then hopefully show that this is a Kobayashi geodensity. Thanks for your attention.